Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And this is joint work with Shipragrawal. So let me begin with some motivation. So Thompson, 1933, first introduced this problem, and his motivation came from clinical trials. So suppose you have a disease for which you have two treatments, but you don't know how effective they are. But the patients are coming to you, and you must administer one treatment or the other right away. So an intuitive thing to do in this case is that you try both treatments for some number of times to understand which treatment is better, and from then on you just administer that treatment. So this problem presents this explore versus exploit dilemma, which is how long do you explore, how long do you try both treatments before you are sure which one is better, and then from then on you start exploiting, you just start to use the better treatment. So this kind of problems arise in many situations, and the multi-arm bandit problem is probably the simplest problem that model for these explore-exploit problems. So this was also done by Thompson. So in this problem we have n arms or actions. You can think of, in the previous example, this n was 2. There were 2 possible treatments. The name multi-arm bandit comes from imagining a slot machine which has n arms, and in each step you will pull one of the arms. But usually slot machines rob you of money instead of giving you money, so that's why it's called a bandit. So anyway, so we have n arms or actions. Each arm corresponds to an unknown probability distribution on interval 0, 1. This is the assumption of interval 0, 1 is not essential, but we'll make this assumption for simplicity. And then at each time step t, starting from 1, 2, 3, and so on, the algorithm has to choose an arm I of t to play. So if the algorithm plays arm I of t, then it gets a reward that's generated according to the distribution for that arm. And this is independent of everything that has happened in the past, the choices that you made and the outputs of those plays of those arms. But the choice that you make in a step, of course, depends on what happened in the past. The goal then is to maximize the total reward. You don't know at what time you will stop, so at any given time you want to be as good as possible. And in this talk I'll restrict to Bernoulli rewards, just for simplicity. We can deal with the more general case of the continuous interval 0, 1. So that's the basic problem. So we want to maximize the reward, but the reward is a random variable, so it's more meaningful to talk about maximizing the expected reward, or we could talk about saying that reward is at least this number with high probability, that kind of thing. But we'll only talk about expected reward, so you want to maximize the expected reward. So if we settle on that, then the only thing that matters about each arm is the mean for that arm. The distribution doesn't matter. So if you knew which arm had the highest mean, then the best strategy is to just play that arm from that point. So intuitively, what an algorithm needs to do, it wants to learn enough information about the arms to find out which one has the highest mean, and just wants to play that. It doesn't necessarily need to learn the means themselves. So we can write the expected reward at time t in this way. So it's expectation over sum is over the arms, I equal to 1 to n, of mu I times ki of t. Mu I is the mean for arm I, and ki of t is the number of times this arm is played in t steps. So ki of t is a random variable, depends on the choices that the algorithm makes and the outputs of playing the arms, and this expectation is over all those random choices. Okay, so we would like to maximize this thing. But it turns out to be more convenient to look at regret, expected regret. So it's closely related to expected reward, but just for convenience, one looks at regret. So regret is just how much we lost in expectation because we didn't know what the optimal arm was. So if the best arm is the arm with maximum mean, mu star, and at time t, if we play arm I, then our regret is mu star minus mu I in expectation. So expected total regret at time t is t times mu star. This is the reward we would get if we always played the best arm, minus the expected reward that we actually got. So which we can also write as sum over I equal to 1 to n, delta I times expectation of ki of t. Then the question we are interested in is how small can this reward be? Can it be little of t? Can it be order square root t or order log t? This is the kind of question people try to understand. Okay. So that's the multi-arm bandit problem, and let me just mention a few more applications before I go to algorithms. So I already mentioned clinical trials. One modern application is to online advertising. When a search engine needs to show ads to a user in response to a query, it would like to show ads which are more likely to get clicks. But in order to find which ads are more likely to get clicks, you have to show them a few number of times. You have to explore before you can find out that probability. So one encounters that problem here. And there are other situations like news article recommendation. You want to show articles which are more likely to be read, but then you have to try them before you know which are more likely to be read. Okay, so let me mention a few well-known algorithms for this problem before I go to Thompson sampling. So one quite popular heuristic is the epsilon greedy heuristic. At time t, what we do is with probability 1 minus epsilon t, play the arm which has the highest empirical mean so far. So in the trials for that arm that have happened so far, you take the mean for those outputs for those and choose the one that's the best with probability 1 minus epsilon t. And with probability epsilon t, they are random arms. So in the second step, we are exploring. In the first step, we are exploiting. So the choice of this epsilon is a tricky thing and requires a bit of tuning. So one good choice turns out to be this. Epsilon t is minimum of, I think I'm missing a t over here. It's 6n over delta square t and 1, where delta is the minimum of all the positive deltas. And this has a regret of some constant times log t. So, but this is not very good because the constant c is quite bad. Its dependence on the parameters of the problem is quite bad. And also one needs to know what this delta is. So probably the most popular algorithm for this problem is the UCB algorithm. It's actually a family of algorithms due to Auer, Cesa-Bianchi, and Fischer. So it's very simple. At time t, to decide which arm to play, we do the following. For each arm, we compute what's called upper confidence bound. So it's the sum of two terms, the empirical mean for arm I, and it's a second term is a regularizer term, which is square root of 2 log t over ki of t. Ki of t is the number of times the arm has been played. So if an arm is good, then mu I, the first term will tend to be high. So you will tend to play that arm. On the other hand, if you have not played an arm enough number of times, then the second term will tend to be high because ki of t is small. So this upper confidence bound is taking care of both exploration and exploitation. It's trying to strike a balance. And it's doing a good job of that because Auer et al. Proved this theoretical guarantee that the regret for this algorithm is sum over I for positive delta I of log t over delta I. And that's pretty good because it's close to the lower bound. Due to Lie and Robbins, which is sum over I of delta I over the KL divergence between mu I and mu star. So this delta I over KL divergence in many situations is not very far from delta I, although it can also be far. So it's of a similar form as the lower bound. So it's getting pretty close to the lower bound. And recently there's been a lot of activity in trying to improve this upper bound and get it close to this, and people have been quite successful. So now there are variants of this basic UCB algorithm, KL UCB, Bayes UCB, in last 2 years, which get almost this lower bound. The way they achieve this is by tweaking that constant factor in the regularizer term, that factor 2. So at each step they carefully compute that constant factor, which requires solving a optimization problem. So the algorithm gets more complicated, but they get better bounds. Okay. So now I'll go to Thompson sampling. So let me say why we are looking at Thompson sampling when the previous algorithms have been quite successful. So this was also given by Thompson in his original paper where he introduced the problem. So our interest is mainly due to some empirical studies which have been performed in the last 2 years. So Chappell and Lee and Kaufman et al. Have done a thorough comparison of Thompson sampling with the various variants of UCB algorithm that I mentioned in the previous slide. And Thompson sampling does better than all of them, at least in the long run. It has other desirable properties, like it's robust to delayed feedback. What that means is you don't get to see the outcome of playing an arm right away, but maybe after 100 trials. So in the example for clinical trials, when you administer a treatment, you don't right away know what happened to the patient. You only get to know that maybe after a month. But you still have to keep making decisions. So it does better in the case of delayed feedback. It's arguably easy to implement, at least easier than KL UCB, Bayes UCB. Extends to more general settings like contextual bandits. I'll mention that in the end. It has been used in an industrial application, and it's easy to incorporate partial knowledge about arms. If you know that an arm is likely to take certain value, if you have some partial information about mu I for arm I, then you can use that in the algorithm easily. Okay. So let me say what Thompson sampling is. Before I do that, okay, let me show you a graph from Kaufman et al. Comparing the performance of Thompson sampling with UCB algorithm. So here the x-axis is the time, y-axis is the regret, and in each case the number of arms is 2 with different values of mu. And you can see that the black curve represents the regret for Thompson sampling. And it's better than the other algorithms, except maybe in the short run. And that probably happens because it's a randomized algorithm and initially it explores more. Okay. So before I talk about Thompson sampling, I need to tell you what beta distribution is. Most of you know what it is, but for those who don't know, I'll quickly try to explain what it is. So beta distribution takes 2 parameters, alpha and beta. It has a distribution with support on interval 0, 1. And if random variable theta is distributed according to beta, alpha, beta, then its PDF is like this. Probability of theta is proportional to theta to the alpha minus 1 times 1 minus theta to the beta minus 1. So if alpha and beta are both 1, then this is the uniform distribution. Okay. And as alpha and beta increase, the distribution becomes more concentrated. So the mean of the distribution is alpha over alpha plus beta, and the variance is this number alpha beta over alpha plus beta square and alpha times alpha plus beta plus 1. So if alpha plus beta becomes large, then it becomes more concentrated. So here is an example. Alpha and beta are both equal in this case. When alpha and beta are both 1, then this is the uniform distribution. And when alpha and beta are both 50, then we get this very concentrated distribution. So the reason beta distribution is useful is because it's a conjugate prior to Bernoulli distribution. What that means is the following. So suppose we have a coin with the unknown probability mu of coming up heads, and we have some prior information on mu, which is that it's distributed according to beta distribution with parameters alpha beta. And we toss that coin, and depending on the outcome, the new posterior distribution is very simple. So if the coin comes up heads, then the posterior is again a beta distribution with parameters alpha plus 1 beta. And for tails, it's the parameters are alpha and beta plus 1. So it's conjugate prior because the prior and posterior are both of the same family. They both are beta distributions. So this is very nice property because it's very easy to update beta distribution, and it's also very easy to sample from beta distribution. And more generally, for this property, we can say that if we start with uniform prior on mu, which is beta 1, 1, and we toss it a certain number of times, out of which S were successes and F were failures, then after that, the posterior becomes beta with parameters plus 1 and F plus 1. Okay, so now I can tell you about Thompson sampling. The actual algorithm will be on the next slide. I'll just give a little bit of preview of the algorithm here. So it's a randomized algorithm, unlike the UCB algorithm, which is deterministic. You can think of Thompson sampling as a randomized version of UCB. And it uses a Bayesian idea, which is for each mu, we maintain a prior distribution of that over, for each arm I, we maintain distribution over mu I. So initially we have no information about what mu i's are. So that we capture that by saying that the mu i's have prior beta 1, 1. And after we have tried an arm I for some number of times with Si of t successes and Fi of t failures, then at time t, the prior for that arm is beta distribution with parameters Si of t plus 1 and Fi of t plus 1. So the mean for this arm is going to be Si of t plus 1 over Si of t plus Fi of t plus 2, which is close to the empirical mean, which is what we would like to happen. And as the number of plays increases, as you try an arm more and more often, then this distribution gets concentrated, as we saw before, and gets concentrated around the empirical mean, and empirical mean gets close to the actual mean. So our information about that arm converges to the right distribution. Okay, so here is now the algorithm. It's very simple. At step t, to decide which arm to play, what we do is the following. For each arm I, we generate a random variable theta I of t according to distribution beta with parameters psi of t plus 1 and Fi of t plus 1. And we play the arm I star of t for which this random variable is the greatest. Okay. So you can think of this as playing the arm which, according to our current beliefs, you can think of it as playing the arm according to its probability of being the best arm according to our current beliefs. So after all arms have been played enough number of times, thetas are going to be close to mu j's, and we will play the best arm after that. All right. So that's the algorithm, and we want to understand its regret. So since if we have played each arm enough number of times, after in long run we play all arms enough number of times, then we will play the best arm after that. And that's captured in this theorem of May et al. The probability of playing the best arm converges to 1 as t goes to infinity, which is same thing as saying that regret goes to 0 as regret over time goes to 0 as t goes to infinity, or regret is little of t. So this was basically the only thing that was known about Thompson sampling. Okay, so now I'll state our results. So we show the case of 2 arms turns out to be simpler. So for case of 2 arms, we show that regret of Thompson sampling is like log t over delta plus 1 over delta cubed. So delta is mu1 minus mu2, and I'm assuming mu1 is greater than mu2. And we can contrast this with the UCB and the lower bound. So we are doing actually worse than UCB, because UCB is order of log t over delta. There's no additive term there. And I'm not bothering about constant factors here. And similarly, we are worse than the lower bound. But we are not too far. And this result gives us a problem-independent bound. So what do I mean by problem-independent bound? So there's a funny feature of this bound, which is that if you make delta go to 0, then this becomes large, which should not happen, because if delta is 0, then it doesn't matter which arm you play. So the regret should be 0 in that case, but it goes to infinity. So really the regret is minimum of that bound, log t over delta plus 1 over delta cubed, and delta times t. This is the maximum regret you can incur. And if you maximize this by choosing delta, then it turns out to be t to the 3/4. So you get a problem, so it does not depend on the choice of delta. So you get a problem-independent bound of t to the 3/4. And for multiple arms, our bounds are slightly weaker. So regret here is sum over I over 1 over delta, sum over I of 1 over delta I squared times log t. So this is weaker than UCB because of delta I squared versus delta I here. It's also correspondingly worse than the lower bound. But it's a start. And we get a problem-independent bound of t to the 2/3. So those are our results. So I'll just describe the proof idea for the case of 2 arms. The case of multiple arms is more complicated. So as before, I will assume mu1 is greater than mu2, and delta is mu1 minus mu2. Simple observation here is that if both arms have been tried L times, L is log t over delta squared, then we are in good shape. What that means is after that many trials, the beta distributions become very tightly concentrated around the empirical means. And the empirical means are close to the actual means with high probability. So theta 1 of t is greater than theta 2 of t with high probability, 1 minus 1 over poly t. So if both arms have been played enough number of times, then we will make the right decision with very high probability and not incur regret. So the question then is, how much regret do we incur before we get into that good situation? So another observation is that whenever second arm is played, then we get a regret of delta, and when we play the first arm, we don't incur any regret. So we can assume if the second arm has been played at L times, then the regret is at most L delta. So we can assume that the second arm has been played at least L times, because if it has been played less number of times, then the regret is anyway L delta, which is log t over delta, which is not large. We can afford that. So then the question is, assuming that the second arm has been played L times, what is the regret until the first arm also has been played L times? So that's the question we'll try to answer. So to answer that, we need to understand this probability that theta 1 of t is less than theta 2 of t, which decides which arm we will play. So here, a big difference from UCB occurs. So theta 1, if the first arm has not been played enough number of times, then theta 1 is not concentrated, it's flat. So there is a good chance that theta 1 will be less than theta 2, and we won't play the first arm. And so we will not improve our knowledge about the first arm, and we'll continue playing the second arm. But because it's flat, there's also a good chance that the first arm will be played. It will turn out to be greater than theta 2. And that's sufficient for us to improve our knowledge about the first arm before we incur too much regret. Okay. So here is probably the main idea of the proof. Let me describe that by this picture. So we assume that the second arm has been tried at least L times, as I explained on the previous slide. Then the number of steps between the jth and j plus 1th trial of the first arm is essentially a geometric random variable. Assuming that S of j is fixed. S of j is the number of successes of the first arm in its j trials. Okay, so let me explain that in this picture. So these are time steps, and the jth trial of the first arm happened here. So theta 1 of t came out to be greater than theta 2 of t. So we played the first arm, and all these steps, theta 1 was less than theta 2, so we did not play the first arm, we played the second arm, and then the j plus 1th happened here. And this interval, the length of this interval we denote by xj, and we would like to understand this random variable, how this behaves. And the claim is that it behaves like a geometric random variable. So why is that? So since we are assuming the second arm has been played L times, so theta 2 of t is concentrated. So for practical purposes, it behaves like mu2. It's concentrated at mu2. But theta 1 of t also behaves nicely. It's random, but its distribution all throughout this interval is exactly this. It's a beta distribution with the parameters s of j plus 1 and j minus s of j plus 1. Why is that? Because at this point, the number of successes was s of j, and the parameter and the theta variable had this distribution. And at each point here, we did not play the first arm, so we did not update the distribution for the first arm. And all throughout this interval, the distribution will remain the same. So the check for playing which arm to play becomes this. We check whether theta 1 of t is greater than mu2, and that's exactly this number, 1 minus f of this expression in terms of beta distribution. So given s of j, if we fix s of j, then xj behaves like a geometric random variable, and that turns out to be very useful. So success probability of this geometric random variable xj, let's denote that by p of j s of j. We fixed s of j, and as we saw on the previous slide, it's given in terms of some expression involving beta distribution, and it turns out to be equivalent to another expression involving binomial distribution. So the details here are not important, but I just want to show this because this turns out to be very useful for computations. Because binomial distribution, we can apply Chernoff bound and that kind of estimates. So this equivalence is very useful. So then we can, expectation of this random variable xj given s of j is by standard formula for geometric random variables, it's just 1 over the success probability minus 1. But s of j is not really fixed, it's random. So we also take expectation over s of j. So here this outer expectation is over s of j. So this is the expression we really want to understand. Okay. So s of j is distributed as binomial. So in j trials, each trial has probability mu1 of coming up heads or of succeeding. So s of j is distributed as binomial with the parameters j and mu1. So this expectation that we wanted to understand becomes this complicated expression, which you don't really need to parse, but well, it gets quite complicated. But after some work, it simplifies. So this expectation, if j is large, then it's very small. It's like 1 over t. But if j is small, then it's like 1 plus e to the negative divergence between mu2, mu1 times j over delta. Okay. So the number of steps where the first arm is not played until j becomes L is just obtained by summing this thing over j from 1 to L. So you just sum this expression for j equal to 1 to L. So this 1 will give you log t over delta square L, and this turns out to be negligible. So this is the number of steps where the first arm is not played until it has been played L times. And each of those steps we incur a regret of delta. So the total regret that we get is L delta, which is log t over delta. So that's why we get that number. Okay, so that's all I have to say about the proof. Any questions? Because I'm going to switch gears from now. Okay, so how much time do I have? 5 minutes. So I'll talk about contextual bandits, which is a more complex setting, but it's also probably more applicable in many situations. I'll just describe a very simple. So contextual bandits have been studied in many different models. The model I'm going to describe is very simple. It's bandits with linear payoff. But before that, let me talk about some applications. So contextual bandits are basically when you personalize your choice, the arm of playing the arm. So in the case of clinical trials, before making a decision about which treatment to give them, we look at their profile, their DNA sequence, and all kinds of things. In online advertising, we can again look at the profile of the user, where they are living, and what's their age, and all kinds of things. And that may allow us to make better decisions. And this is captured in contextual bandit problems. This is one specific model which is quite concrete compared to many other models, but still seems to be quite expressive. So again, n is the number of arms, and at each time step t, a context arrives. By context, you can think of the patient arrives, or a user. In the case of search engine, the user makes a query. So context here will be a collection of vectors. For each arm, we get a vector a1 of t, a2 of t, an of t, which is a vector in r to the d. And these are vectors with of length at most 1. So these features could represent any kind of things. It could be whether the ad that we are showing ad I is relevant to this user. What's the history of the user for this category of ads. So the coordinates in these vectors could be all kinds of features. And then the probability that an ad I will be clicked at time t is just given by this. You take the dot product of ai of t with an unknown vector x, which also has norm at most 1. So this is a new model for contextual bandits. So what is the reward? What is the regret in this case? So if we played arm I of t at time t, and if I star of t is the best arm at time t, which is the arm which had the highest probability, so which maximized ai of t dot x, then the expected total regret is just obtained at time t is just obtained by summing this dot product. This is the reward we would have got if we played the best arm minus the reward that we actually got. So this is the expression we'd like to minimize. So we want to learn x so that this regret is as small as possible. And one can generalize UCB style of algorithms to higher dimensional settings like this and achieve a regret of square root of TD times log n. But again, Thompson sampling seems to do better in experiments. And we have recent results where we show almost matching bounds to the UCB style algorithms. But I will not go into that. So I'll conclude. So very recently, for the multi-arm bandit problem, using our ideas and some new ideas, Kaufman et al. Have achieved the lower bound that I showed you, Lai-Robbins lower bound. So that shows that Thompson sampling is actually optimal. So it's very simple, does not use any parameters, and achieves the lower bound. And let me just mention two open problems. As far as I know, there is no study of impact of delayed feedback, or what kind of guarantees we get in that case. And for linear contextual bandits, I made this realizability assumption that the probability was exactly the dot product. But what happens if it's not exactly the dot product, but it's only approximately equal to the dot product, which seems to be a more realistic scenario. So that's it. Thank you.
Questions?
So would it be interesting to talk about how we define probability in the actual period as opposed to consider the regret?
Yes, you can do that, and we can prove results like square root t. It's like square root t with high probability.